Hi, my name is Wenyuan Zeng. Today I'll present DSDNet, Deep Structured Self-Driving Network. Driving autonomously in a complex environment is very challenging. One of the main reasons behind this is that a self-driving vehicle doesn't know the position and behaviors of other actors beforehand. Instead, it can only rely on raw sensor measurement such as LiDAR point clouds as well as HD maps as we show here. In order to drive safely on the road, it needs to detect surrounding actors in the scene, predict their future behaviors, and then make a safe planning based on the detection and prediction results. Traditionally, people build separate models for each task and sequentially hook them within an inference pipeline. However, in this case, computation is now shared across tasks, which imposes difficulties for low latency inference. This motivates us to use a single neural network to solve all three tasks. Another challenge is that future is not certain. For instance, for this highlighted car, it could either turn right or go straight. Moreover, different actors interact with each other and follow traffic rules, such as yielding and not colliding. Therefore, a socially consistent multi-agent prediction with calibrated multimodal uncertainties is necessary for safe planning. Lastly, a planner should take all possible futures into consideration and ensure the planned trajectory is compliant to other actors' possible behaviors. In this work, we propose DSDNet, a deep structured model that jointly reasons perception, motion forecasting, and motion planning. Specifically, our method has several advantages. First, computation are shared between modules. Second, our method explicitly models socially consistent multimodal uncertainty into the future. And finally, our learning-based planner leverages the power of deep learning and takes rules into consideration as well towards guaranteed safety. Now, let's have a look at how our model works. Given LiDAR point clouds and an HD map as input, we have a neural network to produce backbone features, which will be shared across all our modules. We first use these features to predict detection results. For example, here we have detected 3 vehicles. Our next step is to predict the future behaviors of all detected actors, as well as the uncertainties. This is not a trivial task, as we expect to predict a multimodal, non-parametric distribution which can capture complex situations. More importantly, the behaviors of all actors should be socially consistent. For example, they should not collide with each other. To have an efficient representation for this non-parametric distribution, we first sample a set of dense, diverse, and physically feasible trajectories with different directions and velocities for each actor, and then build a probability distribution over these trajectories. More specifically, we use a neural network together with the backbone feature map to predict a score for each trajectory. As an illustration, the car at the bottom is likely to go straight with different speed, or turn left, or turn right, predicted by our model. Other lighter colors mean low probability behaviors. By doing this for each actor, we have an estimation of the future. However, this does not guarantee social consistency, as the behaviors of actors can potentially conflict with each other. This is because we haven't modeled interactions between actors, such as collision avoidance. In fact, it is actually hard to explicitly encode this prior knowledge in a neural net. Our approach models the interactions by treating each actor as a node in a probabilistic graph and have the edges encode our knowledge about their interactions, such as yielding, collision avoidance, etc. For example, for every pair of actors and every pair of their behaviors, we can evaluate a score of consistency. In this case, and this case, since the actors' actions are consistent, we have high scores, which means good. And in contrast, here we have a low score, since the actors collide. Combining neural network-based trajectory scores and our consistent scores, we conduct an efficient inference using message passing so that low-scored, inconsistent behaviors will have low probability. Finally, our model plans a safe trajectory for the Eagle car by considering the current situation and other actors' future behaviors. We formulate the planning as a cost minimization problem, namely finding a best trajectory among a set of feasible plans. We solve this by first sampling trajectories, evaluating cost for each sample, and pick the minimum cost trajectory as our final planning. To compute cost for a given trajectory sample, we also use a neural network. For example, here, those out of road and unnatural trajectory will be regarded as a high-cost trajectory, and we color them in lighter color. However, this learned cost does not fully utilize the benefits of our predictions. Instead, we hope that the planning can explicitly minimize the expected collision rate given our prediction results. Therefore, we add a structured collision cost. Take this planning trajectory sample as an example. Recall that our predictions are given as distributions over discrete trajectories. Therefore, we can easily compute an expected collision rate as the structured collision cost using a weighted sum. In this case, the structured collision cost will be high because the sample is likely to collide with other actors. And in this case, it will be low. Finally, we combine the network-based planning cost as well as the structured collision cost and find the minimum cost trajectory among all our samples. This gives us our final planning output. Here, we first report our prediction performance. We compare our multimodal, socially consistent prediction method against several state-of-the-art methods on a number of datasets. We show here the results on two publicly available datasets, Musin and Precalc-Harlow. As shown in the figures, we achieve significantly better prediction performance. We also achieve a near-zero collision rate among predicted trajectories, which corresponds to more realistic human behaviors. For planning, we show our comparison against an end-to-end imitation learning baseline, as well as a previous state-of-the-art neural motion planning method, short as NMP here. Our approach achieves significantly better performance in terms of collision and lane violation rates. This is due to the fact that our model explicitly considers multiple future possibilities, and then plans a safe trajectory that is compliant with other actors' future behaviors. Now, let's see some qualitative results. In this figure, each blue box represents a detected actor, and its dotted line represents its most likely future prediction. We visualize the model's uncertainty estimation with a dense color map. Different colors represent different times. This is the uncertainty at 1 second into the future, and this is 2 seconds. We can see that our predicted uncertainty becomes more spread out as the future is more uncertain. Here is 3 seconds into the future. Our model is able to capture all the possibilities for the car approaching an intersection. This is a good thing. It suggests that our motion planner will take all possible futures into consideration when planning its trajectory, not just a single one. Here is one more result on motion prediction. We can see that for far away and turning actors, we are more uncertain of their future. And on the other hand, for actors that are going straight along the lane and close to us, our model is quite certain. Next, let's see some planning results. Here we show a scenario in which our Eagle car follows a curved lane very well. Here is a turning scenario where you can see that our planned trajectory is smooth and follows the lane structure. Here is a short demo. As you can see, our model nicely captures multimodality, especially for vehicles that are approaching an intersection. When a vehicle is driving on a straight lane, our model is more certain about its direction, but a bit uncertain about its future velocity. Here is one example where we perfectly predict that the leading vehicle is stopping, and thus we plan a nudging trajectory to avoid collision with that parked car. In summary, we propose to use a single neural network and jointly perform object detection, motion prediction, and motion planning for self-driving. Our approach uses an energy-based formulation to tackle the multi-agent, multimodal prediction task. Our deep structure planning module can seamlessly work with the prediction and planning it safely under uncertainties. And lastly, We achieve state-of-the-art results on a number of self-driving datasets. Thanks for listening.